So sketching functions, truly is the backbone of the HSC Maths Advanced or even Maths Standard. And it's a topic that I really hated for a long time until stuff like financial maths came along, and I was like, okay, sketching isn't that bad. Um, so you probably will be asked to sketch a graph, but you do need to know how to check um like how to actually sketch graphs. Partially because there's a chance that you will be asked to sketch a graph in the HSC. But also there are a lot of times where sketching the graph is going to actually get you the correct answer, whether or not you're actually marked for sketching it. Which might not make sense yet, but we'll get a few questions in a few slides that will kind of get you there. Oh my gosh. Okay, so how do we actually graph a graph? So there's three simple steps. So first we're going to find the x and the y coordinates and plot them to join the like a dot to dot curve or line. Kind of works. It is very time consuming, and sometimes you might miss the actual point of the um the actual points of turning the actual turning points and stuff. So it's an okay method. The other method is translations and dilations. So you know the actual shape of the curve and you can like move it this way, 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 this way. And then the third way is through finding the first and the second derivatives. The third way we will not be going through this lecture. You'll have access to the January lectures, however, when I did go through this. So if you're not sure how to do it, or if your class has like now started doing differentiation and you want to recap all that stuff during the holidays, highly recommend go to the January lecture. Okay, so oh my gosh, why does it keep doing that? Okay, so what is necessary to have in any graph? So let's say we have like a 5-mark question, and 1 mark will be allocated towards just the actual presentation of the graph. By that, I don't actually even mean the shape of the curve or anything. I'm talking about the requirements to just get everything. So they include the labeling of the x and y axes as well as the origin. The intercepts, if there are any, should also be shown. The equation of the graph should also be labeled as seen over here. And we need an appropriate scale. So that doesn't necessarily mean that your x and your y need to be the same, but your x and your x needs to be the same, and the y also needs to be the same. So an example of what I mean by what you shouldn't do is, let's say we have like -2, -1, 1, 2, 3. And then on this side, we've got like 1, 2, 3, and this is like -100, -1,000,000. Okay, that's 100 million. Never mind. But yeah, you see the point, right? There is no actual uniformity with the x-axis, which you need to have. So something else to keep in mind. If you don't have any one of these 4 things, you will not get full marks in your question. So if you accidentally forget to label your x and your y axes, I'm really sorry, because you just lost a mark for not labeling them. So this is something that I want you guys to get really comfortable doing now, whilst you're still like getting used to drawing graphs, so that you've formed a really good habit. Okay, so let's go into the translations and dilations. So just a pro tip about studying for the HSC. You don't necessarily need to know every single dot point in the syllabus, but you should study from the syllabus. So if your school was anything like mine, especially for maths and chemistry, I had teachers that were super duper passionate about maths or chemistry. And they teach you a lot of stuff that wasn't necessarily related to the content, but just because they love that kind of stuff. So, sorry. Oh, it's bad when I'm losing my voice already half an hour into the lecture. Sorry, but yeah. So just so that you actually know what is required of you guys to know, the syllabus will tell you everything. Nessa can't teach you anything that's not in the syllabus. So the syllabus is your best friend. Would recommend studying from there. So you can see that there's actual like dot points and the kinds of graphs that you can actually like graph as well. So everything required is there for you. Okay, so let's go into translations. Translations is basically moving a graph. So literally, we've got our parabola example over here. Um, Here's our parabola. We can move it up or down. We can move it left or right. Okay, that's what I mean by a translation. So when we're moving a graph up or down, um, we can add c to it. So y is equal to f of x plus c. C can be any number from negative infinity to infinity, but the direction or the value of c is something that matters. So if c is positive, the graph will be translated c places up. If c is negative, it'll be translated c places down. And that is pretty much all to it. So I'm going to give you a second to try this on your own. So draw y is equal to x squared. And then on the same graph, draw y is equal to x squared plus 5, and then x squared minus 4. Yeah, okay. You'll probably need a little bit more time than this. So what I'd recommend is just pausing this video and graphing the rest of your curves. Please remember to actually try and incorporate the 4 things that I was talking about in the previous slide that are going to get you your full marks. So definitely something that I want you guys to get used to now. Okay, so this is what your curves will look like. I'll give you a second to try and see what am I missing in these curves that's going to stop me from getting full marks in if this was like a HSC question. I'll give you a few seconds to think about it. If you made notes on what I did like 3 slides ago, you'd be able to point out quite a few things. Okay, I'm going to assume that you guys know now. So, stuff that I have not incorporated includes my x and my y axes labeled. My origin is already labeled. I need to have my intercepts labeled. So this one's nicely labeled, this one's nicely labeled, but this one over here, I just need to write it's -4. I also have my x-intercepts labeled. I've only got 2 x-intercepts, and luckily for me, y is equal to x to the x squared minus 4 is something that I can figure out the intercepts for. So let's figure it out. The way that we can figure out our intercepts is by making y equal to 0. So y is equal to x squared minus 4 is equal to 0. X squared is equal to 4. So x is equal to plus or minus 2. So this over here is minus 2. This over here is 2. Awesome. Now what else is left? I need to actually label my curves. So in the blue, we have y is equal to x squared plus 5. In the red is y is equal to x squared. And in the green, we have y is equal to x squared minus 4. Okay, awesome. Perfect. Okay, now let's move on. The other kind of translation that I was talking about before was left and right. So that can be seen for the notation y is equal to f of x plus b. So I want you to take a look at the actual notation. You can see that we've got it inside the brackets of the function, as opposed to y is equal to fx plus c. Y is equal to f of x plus c. The way that I remember which variable is being impacted by these translations is by actually looking at where the like B and the C actually are. So if you take a look at your C over here isn't actually inside with f of x the same way that B is. So C, if it's not related to x, it would need to be related to y. So it's outside the brackets, it's related to y. In this same way, our b is in the brackets with with x, which means that it needs to be related to x, right? So it's not really dependent on the y. So b is horizontal translation, whilst c is a vertical translation. For many of you guys, this would be very simple stuff, but I just want to make sure I go through this for someone that might not be super confident with this because we've got a whole range of people with us today. Okay. Now the actual impact that B has on the translation. So B can, as I said before, moves it left to right. So B can take any real number, um, ranging from negative infinity to infinity, just like C. But the actual value is kind of counterintuitive compared to C. C is pretty easy. It's like if C is positive C, then we're moving up C places, right? In this case, if B is negative, then we're moving to the right by B places. And if B is positive, then we're moving to the left B places. Okay, so right is negative, left is positive. Um, the way that I remember this, it'll come a bit more handy even when we go into our dilations, is that X is always counterintuitive. Whatever you think it is, chances are it'll be the opposite. So if something is negative, typically you're wanting to go left because left goes to negative sides. But no, we're going to the positive direction. We're going right. So just something to keep in mind because I'm gonna go through that idea in a few slides again. All right, awesome. So now another graphing example. Draw y is equal to x squared. And on the same graph, draw y is equal to x plus 2 squared and x minus 4 squared. I'll give you a sec to draw that on your own. Please try and include the four things that are in a good graph. Okay, I'll give you a few seconds to pause if you aren't done, and we'll move on. So let's take a look. This is what our final answer will look like. Once again, I'm missing a few things in my response, so let's go through this. I should put arrows on all my curves. Tis a standard. I should label my axes and my origin. I should label my intercepts. Luckily for me, the intercept's already labeled really nicely. What else do I need to do? I need to actually label my curves as well. So let's take a look at these graphs. So y is equal to x plus 2 all squared. That means that x plus 2, b is equal to 2. So, well, positive 2, let's keep that in mind. Positive means we're going in the left direction, okay? So if we're going left and we're going two places, our intercept will be x is equal to negative 2. So this blue curve is y is equal to x plus 2 all squared. y is equal to x plus 2 all squared. Our red is our original y is equal to x squared. And now let's take a look at this one over here. Our b is equal to -4. B is equal to -4. Um, so B in this case is a negative number. Negative means we're moving to the right. And by how many places? 4. So our new intercept for x will be at x is equal to +4 because we're moving 4 places to the right. Luckily, the intercept's already written down, which shows that the green graph is our final answer. So y is equal to x minus 4 all squared. And that is everything required to get full marks for this question. Awesome. Okay, now we have something that I suppose is a little bit more annoying. It's something called a dilation. So a dilation means that the graph is either expanding this way, or contracting, going inwards. So let's take a look. Okay, so when we are doing a contraction or expansion, we have two options. So y is equal to k times f of x, or y is equal to f of kx. Now this is a little bit different to your normal examples, because I'm not sure, let me check. The example given won't really go into this too much, but we will go through like proper examples later on. I'm actually going to change the value of k over here to a, just to make your lives a little bit easier. So let me go through k first because k is correct over here. So k is a vertical dilation. So it's being, the curve, whatever it may be, is being stretched by a scale factor of k. K can be any real number, just like C and B, sorry, between negative infinity to infinity. K means that the whole curve will be expanding slash contracting. It'll expand if K is, yeah, okay. It'll expand if K is between 0 and 1, or even more so between, if the absolute value of k is between them. It'll contract if k is greater than 1, and it'll flip over the x-axis, so it'll become negative if k is negative. Now let's take a look at a, because a is like the complete opposite of that. Basically, if we're impacting k, we are making it become super long. If we're impacting a, we're changing its width. So let's go through this. Okay, a can also take up any number, and it will expand or contract the curve using the x sides and not the y sides. It will contract if k is between 0 and 1. I'm going to write it as -1 to 1, because any of those numbers, the absolute value of k will be less than 1. It will expand if k is greater than 1, and it'll flip the y-axis. Oops, why am I writing k? I should be writing a. Sorry for anyone that's copying. It'll flip the y-axis if a is negative. Okay, so instead of flipping the x-axis like before, we'll be flipping the y-axis. So let's say we have our original curve looking like an exponential. Our new curve will look like this. Okay? So with that in mind, this example, you can choose which one you'd like to use, A or K, and answer these parabola questions. So using the same correct techniques necessary to get full marks in your graphs, draw y is equal to x squared, and on the same graph, y is equal to a half x squared and y is equal to 2x squared. I'll give you a second to do that. Okay, a few more seconds. Okay, let's get started. So let's work through. Oh, go away. Let's work through this question and this question. Let's do the first one. So y is equal to a half x squared. So my k value is equal to a half. So what's going to happen to the actual curve? We've got a dilation by a scale factor of half, aka our curve, which might look like this, it's going to be squished. It's going to become a half the height that it actually is. So just really quickly drawing, if this is our original curve, then our new curve is going to look a little fatter. Oops, that looks really gross. Like that. Okay, now let's do y is equal to 2x squared. My k value is equal to 2. So if my curve looks like this, my new transformed graph will look like this. So we have my original function and my new function. Okay? And then drawing it with a graph because it looks a bit nicer. If our original function is in red, so y is equal to x squared, the one that is looking taller will be our y is equal to 2x squared because our k factor is larger. And the one that is looking a bit stoutier and wider will be our a half x squared because it's been squished. Awesome. Okay, and then in terms of what we're missing, we just also need to add our axes. Perfect. Okay, now let's go into asymptotes. Asymptotes are something that are a little bit of an odd thing. So what actually is an asymptote? Let's start with that. I'll give you a second to think about and write down a definition of what you think an asymptote is. Okay, I'll give you like 10 seconds or something. Awesome, I think that's about 10 seconds. So an asymptote is something that pretty much the curve will try to approach but never actually reach. It's like a massive love tragedy that like never ends. Um, so an x asymptote could look a little something like this, where it'll try and approach the y-intercept, but it just never will get there. And then a vertical asymptote could look a little something like this, our exponential graph. It over time will try to reach the y-axis, but it will never reach y is equal to 0. So that's what an asymptote is. So a point where the curve will, approach but never reach. So ways that we can work out the asymptote is to inspect what happens as x gets really large. So you can substitute a massive number, both positive and negative, for your x values into the calculator. My personal favorite, which I just have always used, is 6 times 10 to the 6. It's big enough to make things work. And it'll help you see the direction in which your curve tails. Yeah, okay, cool. So an example could be, let's do our horizontal asymptote again of the exponential graph. Let's say I just have no idea what the exponential graph looks like, and I definitely didn't just draw it 20 seconds ago. So in our calculator, we can do e to the power of, let's go 300 because, 3 times is even too big. Let's do 30. E to the power of 30 is equal to 13. So what we can write is, as x approaches infinity, y approaches an even humongouser number. It's 10 to the power, 1 to the power of 13. So 1 times 10 to the power of 13, which is also infinity. So as we get a huge x number, we get an even bigger y number. Now let's go as x approaches negative infinity. What will happen? So let's go e to the minus 30. I get an absolutely minuscule number. I get 9.4 times 10 to the negative 14. So what I can write is that my y will approach 0. To be a little bit more specific even, I could say that it approaches 0 from a positive side. So what I can write is 0 plus. And what I mean when I say by a positive side, if I put into my calculator, I get positive 9.4 times 10 to the negative 14. So it's still a positive number. It's trying to get to 0. It doesn't get to the negatives at all. So it's approaching 0 just from a negative side, which helps me see the actual general curve of the graph to look like this. With an asymptote, because it never reaches 0, but it tries and tries and tries, we have an asymptote at y is equal to 0. Okay? Now we can investigate what happens as x approaches a vertical asymptote. So actually, let's first take a look and see how we can identify a vertical asymptote. The most common way that you can identify a vertical asymptote would be for curves that are reciprocal functions, such as 1 on x minus 2. Okay, that's my example function. I will have an asymptote when my denominator is equal to 0. I'm sure most of you guys have, been like, hey Siri, what's 0 divided by 0? And she'll give a really depressing answer about how you have no friends, and then you start crying about life. But basically, the denominator in a fraction can never be equal to 0. Chuck anything into your calculator on 0, you'll get undefined. So it's just against the laws of physics. So our denominator, x minus 2, can never be equal to 0. So my x value can never be equal to 2 because then the universe will explode. So I'll have an asymptote at x is equal to 2. So I can write, we have a vertical asymptote at x is equal to 2. Okay. Cool. So we can actually take a look at what's happening to the curve as we approach these, like this asymptote. So let's take a look. So I've got to draw it a bit more like this. I have my curve, and then I have my asymptote at x is equal to 2. Okay. Calls. Okay. So I'm going to take a look and see what will happen if I substitute just left of 2. So like 1.99999. So we'll go 1 on 1.99999 gets me to like 0.5. Okay. So at x is equal to 1.999, I'm getting 0.5, which I'll put as like over here. Okay. As x approaches 2.000000001, it also approaches a half. Okay. So what my curve might look like. Oh, I'm sorry. I now realize why my thing's not working. It's because I forgot to write -2. Okay, sorry. Let me redo this. So 1.9999999 minus 2. Okay, so on the left-hand side, we're getting minus like 10 million or something. So I can write as x approaches 2, I'm going to write from the negative side. So from the left-hand side, y approaches minus infinity. As x approaches 2 from the positive side, y approaches, let's find out, 1 on 2.0000001 minus 2, like 100 million. So positive infinity. So my curve will look a little something like that. Okay, cool. I am not doing well for time, so I'm going to kind of hurry up now. So actually drawing the curve. So first recognize the actual type of curve that we've got. So it could be a parabola, a hyperbola, an exponential graph, a log graph. Get familiar with the actual notations for these because it will help you like a quadrillion times more. Then determine actual intercepts and asymptotes. Determine stationary points by doing the first derivatives, points of inflection as well. You may be told if a curve is odd or even, which is something that you went through in year 11. So this, if it's going to be asked, will be given in a question that will be a lot harder than just you have an odd function, draw it. So also keep these in the back of your mind. So an odd function is defined by f of negative x is equal to minus f of x, and even is f of negative x is equal to f of x. So even has an axis of symmetry about the y-axis. So think of like a parabola. Pretend it looks pretty. And then odd has rotational symmetry about the origin. And it must pass the origin as well. Okay? Okay. Cool. Okay, I'm going to give everyone a sec to do this question because it's a really nice question. So draw y is equal to 1 on x squared minus 4. On the same graph, draw y is equal to y is equal to x minus 3. How many solutions does 1 on x squared minus 4 equal to x minus 3 have? Okay, I'm going to give you 30 seconds. Actually, no, I'm going to give you like 10 seconds and then you can pause the video. Yeah. Awesome. Let's take a look. Okay, so this is what the curve. Why does it keep doing that? Please stop, please stop, please stop. This is what the curve looks like. So we have asymptotes at y is equal to x is equal to plus or minus 2. For those of you that weren't sure how to actually draw y is equal to 1 on x squared minus 4, what you're going to do is you're going to go y is equal to 1 on x squared minus 4. Now, the denominator can never, ever, ever be equal to 0, as I was explaining in previous slides. So x squared minus 4 can never be equal to 0. X squared can never be equal to 4. So x cannot be equal to plus or minus root 4, which is 2. So we have asymptotes over here and over here. Okay, next step would be to see what the behavior of the curve is as it approaches these asymptotes. So as x approaches 2 from a negative side, check it into your calculator, you'll get x approaches, y approaches infinity. If it approaches negative 2 from a positive side, you're going to get x approaches negative infinity. Likewise, if we're doing x approaches positive 2 from a negative side, it will get y approaches negative infinity, and x approaches positive 2 from a positive side, y approaches positive infinity. Now, that all sounded like gibberish, so I apologize. And then we have the drawing of y is equal to x minus 3, which I think most people should be comfortable drawing. If you're not comfortable drawing, it is, got a gradient of 1, and we're just translating it 1, 2, 3 places down, and then drawing it. Okay, yeah. Okay, now the actual question is, how many solutions does this have? We have, well, it got cut out, but there's actually a solution over here, one solution over here, and one solution over here. So therefore, we have 3 solutions all up to our question. Okay, here is, oh, okay, never mind, never mind, never mind. Oh, please stop. Okay, sorry. Here's another question. I am not going to go through this question unless we have more time at the end, just because I really want to spend some time on financial maths, and this is all kind of revision for you guys. But this is the question that you can do in your own time. Okay.